Hi, hi, hi. Okay, so last time we finished off the section on isomorphism, and we learned that the representation map gives us an isomorphism between the two spaces, whatever space it is we were working with, and some real n space. So the way the representation map works is that in the domain you fix a basis, and then you take the representation of vectors in that domain vector space, and that gives you an association with Rn. So we'll see that here on the check-in. So the domain space that we're working with is the quadratic polynomials, and I fixed a basis. I just made up a basis. I don't know, I just made one up. So x squared plus x, and x squared plus 1 is three different quadratic polynomials, and you can check that it's linearly independent and that it spans the space. The basis that I'm working with for R3 is the standard basis, and I'm going to look at a particular quadratic polynomial and ask what's it associated with. The representation map associates this quadratic polynomial with which 3-tall vector, and then question 2 asks the reverse question. If you have a 3-tall vector, what's the member of, if you have a 3-tall vector, what's the member of the domain that is associated with it? Okay, all right, so let's have a look. So let's see if I can remember what the parts are now that I clicked away from it. So B is, it's x squared plus x, and x squared plus 1. And then, of course, the D is the standard basis, which I know a person remembers. But anyway, just to have written it down. Okay, oops, doesn't quite all fit on the screen. Okay. All right, and then I want to remind a person again how the representation map goes. The representation map with respect to a basis B of V says this: find the ABC so that V is equal to A times the first thing plus B times the second thing plus C times the third thing. And when you do, the representation map takes V over 2 ABC. Okay, so we're thinking of representation as taking domain elements over to R3. All right, so the instructions up here tell a person exactly what to do. I happen to be given, I wrote it down because I knew I'd forget, -1, -2x, and plus 4x squared. So all I got to do is figure out what A, B, and C are in this expression. A times x squared, B times x squared plus x, C times x squared plus 1. I figure out what A, B, and C are in that expression, and that'll give me the 3-tall vector. That's it. Now, obviously, I could set up Gauss's method. I could set up a linear system, do Gauss's method, come up with answers. But as we've talked about before, nobody made it a crime to be able to look at a problem and see the answer. And I think this is one of those, which is why I chose this basis, because it has that property. So if you look left side, right side, you'll notice that on the right side, the only term that has a constant in it is the third. So from that, I get that C is -1. So by inspection, by looking at the darn thing, you see that C is -1. Likewise with the x's, it was a -2x and a bx. That's it for x's. So b must be -2. And then combining those two, once you know C is -1 and b is -2, you can figure out a. So let's see, -1 and -2 is how many x squareds I have so far. So I must need 2 x squareds to cancel them out. So a is 2. 2 and -2 and -1. Oh, 4. Sorry, I messed that up. So C is -1, B is -2. That makes a total of -3. So I need A to be 7. Whoops, sorry about that. 7. Is that what I wrote down? That's what I wrote down. Oops. Sorry about that. Okay, so what's happening here then is that the representation with respect to the basis b, minus 1 minus 2x plus 4x squared is, the member of R3 is got to put them in the right order, 7 minus 2 minus 1. Okay, and the flip of that, the inverse of that, is just the flip. So instead of starting with minus 1 minus 2x plus 4 squared, instead of starting with something from the domain, you start with something from the range, and you just ask yourself what's going on. So we're asking here, what is it that maps under representation over to its minus 1 minus 1 2? Okay, and the answer simply is v is equal to minus 1 times, where is it? It's up here. There it is. Minus 1 times x squared. Minus 1 times x squared plus x. And c is 2 here. X squared plus 1. And if you can read the handwriting and work out what the heck is supposed to happen, I think I've got minus x squared, another minus x squared, 2x squared, so I think I get 0 for x squared. I've got minus x, so minus x and a plus 2. Okay, so v is plus 2. Okay, so the idea again is that if you fix a domain basis, then the representation takes you back and forth between three tall vectors, in this case because the domain basis has size 3, between three tall vectors and the vectors in the space that you're interested in. So we can represent what we're doing by working with three tall vectors. Well, of course, what we're doing for real is we're really working with polynomials, but we can represent it in some way by working with three tall vectors. Okay, very good. Now, last time we talked about the fact that we are going to start something new. This is a new second section of the third chapter. So the new thing is, in some sense, easier than the old thing. Isomorphism has two different properties. First of all, it's a correspondence. Second of all, it preserves linear combinations. Homomorphisms will have only one of those two properties, and so in that sense, they're easier than isomorphisms. However, homomorphisms are less conceptually clear than isomorphisms. When a person is working through chapter 2 on vector spaces, at some point you say to yourself, wait, the three tall vectors and the three wide vectors, it's the same thing. It's just a typographic difference. You have two spaces, but they're really the same space, just in some kind of disguise. Well, you've surreptitiously discovered isomorphisms. Of course, you have to write all that down officially, and you have to check that you understand the parts and everything. But nonetheless, there's an intuition there that everybody gets at some point in the middle of the second chapter. Now, with homomorphisms, the way we're developing is we're going to start with isomorphism and we'll drop the condition of correspondence. But we have to explain, as we work through homomorphisms, we'll have to explain the significance of what they are. What do you get when you do that? Because it's less clear. So isomorphisms are in some sense easier than homomorphisms because they're conceptually more clear, and that's why I've put them second. But a person can also, sort of strictly mathematically speaking, say homomorphisms are in some sense simpler because they have fewer conditions. But that turns out not to really be true in terms of understanding. Anyway, all stuff that doesn't matter for doing the homework. So for homomorphism, the definition of a homomorphism is a function between vector spaces that preserves addition, and of course we've seen the preserves addition definition before, and preserves scalar multiplication, and again we've seen that before. It's called a homomorphism or a linear map. Those two terms are both very widespread, and I'll try to, maybe not exactly, strictly speaking, alternate from one to the other, but often use one and often use the other. Homomorphism or linear map. Okay, and we have seen a number of homomorphisms already because every isomorphism is automatically a homomorphism. It's a homomorphism with extra special conditions. Extra, comma, special conditions, I guess, comma. Anyway, but so we've already seen a bunch of examples. Of course, we're going to see some more. I'm looking at two different functions from R2 to R. One of them is a homomorphism. One of them is not a homomorphism, and a person does spot the same sort of thing that you started to catch on to, I think, for isomorphisms, that this plus 1 is going to cause you trouble. 2x minus 3y is a linear map or a homomorphism. 2x minus 3y plus 1 is not going to be a linear map or homomorphism. So the map H respects addition we've been doing this for a while now, so I think it's reasonably routine. H of vector 1 plus vector 2 equals h of vector 1 plus h of vector 2. And the steps in the middle, again, we've gone through a bunch of these, so I don't think I need to hammer on these. The map H also respects scalar multiplication. R times h of v is h of r times v. And again, we've done a bunch of these. Don't get me wrong, I'm not embarrassed about what I wrote, but we've done a bunch of these. I don't think a person is going to say, what are you doing here? Because we've seen it a bunch of times before. The contrast is that G does not respect addition. In order to show that G does not respect addition, the most straightforward thing to do is to produce two vectors where G of V1 plus V2 is not the same as G of V1 plus G of V2. And to tell you the truth, that any two vectors you write down, the first two vectors that come to mind, and that's what I did. I just wrote down the first two vectors that came to mind, and it turns out you get minus 17 in one case and you get minus 16 in another, and it just doesn't work. So what works for H here just doesn't work for G, and a person is right in suspecting that the minus 1 is the troubling aspect. We already have some results that we're carrying over from isomorphisms. The first is that we said that an isomorphism sends the zero vector to the zero vector, but if you examine the proof, we never used that an isomorphism in the correspondence, so the same proof works here. So any homomorphism or any linear map, the two words mean the same thing. I'm going to try to use them sort of one and the other so a person gets used to both of them, sends the zero vector to the zero vector. And then the other result we saw that, again, doesn't use correspondence, so it just simply carries over to here, is that if you have a map from V to W, it's equivalent to say it's a homomorphism, or to say that it respects linear combinations of two vectors, or to say that it respects linear combinations of n vectors. Okay? Where n is greater than 1. So those three things are the same thing. It's often the case that we use two, and we've used two a couple times already in the last video, for example. So just really trying to have a whack at some examples. We're going to do some examples this time, and then we'll just take a break just to not have too much in one video, and we'll do some more results and examples in the next video. So between any two vector spaces is a zero map. The zero map takes any input and maps it to W, and it's sort of trivially true, but it's nonetheless true that it's a homomorphism. It's a linear map. So just to check it with case 2 here, the zero map applied to C1V1 plus C2V2 is equal to the C1 times the zero map applied to V1 plus C2 times the zero map applied to V2, and that's just because 0 equals 0 plus 0. That's all. It's nothing complicated. So started off with an example that's simple, maybe too simple to be enlightening. Here's another example, again, just trying to have some examples that we have not already seen. So some examples that are not isomorphisms, just to illustrate something new. So I have the inclusion map. That's an iota. It's not the letter I because it's missing the little dot on top. It doesn't have that, so it's a Greek letter iota. Anyway, the inclusion map from R2 to R3 takes two tall vectors and makes three tall vectors. Outputs three tall vectors, and that's a homomorphism. The verification, we've done the verification for isomorphisms an awful lot, so this is just not going to be a surprise to anybody. If you apply iota to a linear combination, then you get the linear combination of the iotas. I'll go through the steps, but it isn't anything we haven't seen before. The inclusion map applied to C1V1 plus C2V2. Well, add inside the parentheses to get that the first component is C1x1 plus C2x2, and the second component is C1y1 plus C2y2. Next step, you apply iota. It's the same thing, only it's got a 0 on the bottom. Next step, you split those along the plus sign. Of course, 0 equals 0 plus 0. Of course, the third entries work out. And recognize this as C1 times iota of E1, and this as C2 times iota of E2. That's all. So very routine in the light of having done a bunch of them in the context of isomorphism. Now here's one that I think is new and interesting, I think. Okay, it says the derivative function, the regular derivative function from calculus 1. is a transformation. It's a function on polynomial spaces. It takes one polynomial space and outputs another polynomial. So it takes vectors, for example, takes quadratic polynomials and outputs linear polynomials. I'm writing the derivative as d dx. I just don't want to fool around with primes, so I wrote it as d dx. And everybody knows, everybody who's watching this video, knows that d dx of ax squared plus bx plus c is 2ax plus b. And I don't have to explain why 2ax plus b is an interesting formula. A person that thinks about the slope of the tangent line, all this kind of stuff. And anyway, that's a perfectly legitimate formula that a person uses all the time. Just reminding somebody that the derivative of 3x squared minus 2x plus 4 is just exactly what it is in Calculus 1. Derivative of x squared plus 1 is just exactly what it is in Calculus 1. This is the Calculus 1 statement. I haven't made anything tricky at all. I'm observing that it's a homomorphism. That if you apply this function to a linear combination of quadratic polynomials, the result splits along the plus sign. Brings out the real variables. I'll go through the steps, of course I will, but you already know this. It's just that I'm pointing out that homomorphism, linear map, is something you've seen in another context, and so it's at least not totally unfamiliar. All right, let's see how I do. So d dx applied to the linear combination r1v1 plus r2v2. Okay, I broke things out by x squared, x, and constant term. Because when you take the derivative, that's what you want to work with. We know how to take the derivative of an x squared type of thing. You take the 2 and move it down in front. I don't know, you don't actually move it. But anyway, you rewrite this as 2 times coefficient times x. What happens over here? Well, you drop the x. You just write the coefficient. What happens over here? You drop it. It's gone. That is to say, you follow this formula. Okay, well, I can go from this line here to rewrite it to say 2r1a1x plus r1b, 2r2a2x plus r2b in the usual preserves linear combinations way. And then recognize that as r1 times d dx v1, r2 times d dx v2. So the familiar derivative is, in fact, one of these functions. So these functions are something that, you have some familiarity before. You've been using them to some extent before. They didn't come completely out of left field. Another example, the previous one was, I hope, was familiar to a person. Now this one is going to be, unfamiliar to a person. So the trace map takes 2 by 2 matrices and outputs real numbers. And I'm not going to explain where it comes from, because the point of this example is that there's all kinds of things that you haven't seen that are also linear maps. So the trace function on a, b, c, d is a plus d. Now, with derivatives, I didn't think I needed to go in and say, why was derivative interesting? Well, with trace, I'm refusing to say, why is trace interesting? Then my point is that there's a wide collection of things, some of which you know, and a whole pile of things you don't yet know that are also linear maps. So here we go. Trace of a linear combination is a linear combination of the traces, and it works just exactly like the others. One of the things I want to emphasize here and in the next video is that these are actually familiar, in part because we did it in the first section of the 3rd chapter, and in part because some of them you've seen before. Okay, so what happens when you take r1v1 plus r2v2, and we've seen this before. You start out by combining inside the parentheses. Apply the trace map to you add the upper left to the lower right. There's the upper left, there's the lower right. So again, the point of trace is it adds the upper left to the lower right. So there's the upper left, there's the lower right. I gathered together the things with a subscript 1. I gathered together the things with a subscript 2. And that gives me the linear combination. So, if this was the first day of doing isomorphisms, I'd need to go extra slow and make sure I walk through exactly what happened at each step. But a person has done a lot of problems like this in the homework, so I'm figuring that we're good with that. Okay, so we've seen the definition of homomorphism, and we've seen a number of examples, and the theme of the examples, I think, is that some of these are familiar, some of these are less familiar, but all of them work like the isomorphism examples that you've seen before. Okay, and then next time when we come in, we're gonna start learning something about homomorphisms work, about the mechanics of how homomorphisms work. So that'll just be simply more of the same, trying to do more examples and understanding what's happening. Okay, all right, see you then. Very good.